Yes, we can see your screen.
Okay, can you hear me? I mean the voice.
Yes, all fine. You can start.
Okay. I'm Zheng Liangzhen from the Zenix Biotech, Shanghai. So I will introduce the transformer-based deep learning model for the protein ligand binding in CASP15. The main idea here for the protein ligand complex prediction in our three teams is the core scoring function for ligand selection. So the idea is to find a way to generate a lot of different protein ligand binding decoys and use a scoring function or a deep learning model to select the best scoring pose for the final submission. So before we start the CASP15 preparation, we note that the protein structure is not provided. So we are thinking about use a way to generate the protein receptor structure. Obviously, AlphaFold2 is the first come to mind. So we collect all the protein ligand complex structure from the PDB data bank. From the PDB data bank, we have around I think 100K samples split into chains of the protein ligand pairs. So for those number of pairs, we convert the PDB structure, I mean the protein structure, into protein sequences. For those protein sequences, we use our fast AF2 version to build the protein structures. So starting from the AF2 predicted structure, we redock the ligand into the binding pocket. And obviously, before we do the docking, we need to define the binding pocket. So we use a deep learning model called the point size method to predict the per atom probabilities of the protein ligand binding pocket. In the meanwhile, we also do blind global docking. I mean, we suggest that we sometimes do not know the specific binding site, so we do global docking. So for both local docking and global docking, we generate a lot of decoys for one protein ligand pair. So for those kind of decoys, we collect a lot of this data to train a transformer-based model. For this model, the input is the protein ligand complex decoy. Especially, we divide the model into the ligand encoder and the protein encoder. So after the ligand encoder, we get the atom features and the pairwise features. For the protein encoder, we also have the single features and the pairwise features to build a contact map, similar into the protein prediction problem. We construct a atom-wise contact map. So from this contact map and the complex feature combined by the single features into a transformer block, then into the ligand deviation predictor and the structure module. For the ligand deviation predictor, it predicts the per atom RMSD deviation of the ligand structure referred to the original native pose. For structure module, it predicts both the protein structure as well as the ligand pose inside the binding pocket. So this module is a more refined complex prediction module. And for this module, the information is recycling back into the protein contact map and then combined with the previous protein ligand per atom contact into the transformer. So here for the recycling part, the thinking, the idea behind is more or less similar to the AlphaFold2 deep learning model. So for this model, although we have the refined complex structure module, but it is not used for final submission. Only the per atom deviation predictor is used for scoring this ligand pose. So why do we need this refined structure module? The idea is with this supervision of this module, the per atom deviation predictor could be more accurate. So once we already have the deep learning, the neural network-based scoring module, we construct a full ligand pose prediction protocol. The input is the AlphaFold2 structure prediction. So given a protein sequence, we use AlphaFold2 to predict the protein structure. Then we use the pocket prediction method point site to predict the pocket. So once we load the structure as well as the ligand binding site, we use hybrid docking protocol to generate decoys. So in this hybrid docking protocol, we combine the global docking with local docking using orthogonal, SMINA, as well as other docking methods like the iDoc and a different scoring function used in SMINA. After we generate a lot of decoys, firstly, we use the deep learning methods previously introduced already, the transformer-based model to score all of the docking poles and select the best 20 decoys. We perform a clustering analysis by comparing the RMSD between the different decoys. After that, we visually inspect the models and select the 5 model for final submission. So in the blue box, the protocol is for the ligand 1 team. For one more step, given a final model generated by docking methods and selected by the deep learning model, we do local optimization of the ligand pose by a deep RMSD methods. So in this deep RMSD methods, it's a orthogonal scoring function combined with a deep learning scoring function to optimize the frame-based ligand pose. Sometimes it provides better optimization results. Sometimes it did not. So we select the pose according to the deep RMSD with VINA scoring methods. In this protocol, we combine different docking methods with deep learning methods and the optimization protocols to generate final models. Next, I will give some examples about the right predictions and the wrong predictions. So for this target, T1186, the F2 predicted structure is very high accuracy. You can see the green color is the native structure. And we also can find a template from the database, PDB database. And the AF2 could predict the structure with a 0.3 angstrom difference, although the side chain could be somehow misorientated like this arginine. But this residue does not affect the final prediction very much. So we use docking and deep learning ranking and clustering. We can find a docking pose in the gray color. The green color is the native pose. You can see the aromatic ring here is more or less the same, but here there is a 5-member ring part. It's misorientated, but the final group is also somehow okay. So in this example, highly accurate AF2 structure is very important and also helpful. Some of the side chain may affect the final result, but not in this case. In this case, it's okay. But in the next case, the side chain is somehow related to the final model accuracy. For this example, T1124, we can also find a template, but the template quality is not very high. Compared to the native structure, the side chain of this aromatic ring, as well as here, the ligand rings are somehow not very similar, but the pattern is clear. the pi-pi stacking between the rings is a very strong signal. So in our prediction, we also use AF2 to predict the structure. The overall, I mean, the global similarity between the native structure in green color to the cyan color, AF2 prediction structure is 1.3 angstrom. But when come to the pocket, the structure is somehow shifted. The native color is green and the AF2 predicted is cyan. So you can see the structure is overall is somehow left shifted. When we compare the SAH ligand pose, the structure is also somehow shifted towards the left. But we align the structure using the global MST, not the pocket MST. For this example, the side chain orientation is important. The green color show the native side chain, but AF2 predict in the purple color. You can see they are not in the same horizontal surface. They are not in parallel. So we manually rotate the side chain of the aromatic ring to the gray color before we load the final structure. I mean, before we load the native structure, we think this purple ring may not be good enough. So we manually rotate this side chain to make it somehow more reasonable. So without this orientation change, the SAH cannot be well docked into the pocket after we manually change the side chain. So you can see the gray color is the docked pose. It's more or less in parallel with the green color, the native pose. So in this example, it emphasizes the importance of some side chain of the protein, especially like the direct pi-pi stacking systems. Next, I will introduce a wrong case. I mean, in this case, firstly, the F2 could not well predict the trimer. So we use F2 multimer to predict the overall trimer. But the overall trimer for the half part, for the upper part of this domain, the 3 domain could not form a well-folded trimer structure. So when we do docking, the ligand could somehow insert into the trimer interface. So this is the green color is modeled by docking. So we're using global docking as well as a local docking. Obviously, the ligand could not find the binding pocket. We also check all other groups. We find that more or less, it will be hard to find the specific binding area among the 3 monomers, I mean the trimer structures. So in this case, we think the ligand binding sites sometimes could be hard to locate, especially when no template information could be found. So come to the conclusions. The protein structure and the ligand structures are modeled separately. And in some cases, the pocket side chain orientations are important. And the binding site prediction could remain as a very hard challenge, especially when low template could be found. And in our methods, deep learning based model could enrich the template decoys, but sometimes visual inspection is still useful and important. And in our methods, we also use template based modeling for ions, for metal and ions modeling, because for these small molecules, very small molecules, docking could not find the good binding pose. So we use template-based modeling for metal ions. And finally, I would like to thank many people in our teams, like the Shen Tao and Liu Fuxu, the 2 teammates. They build the deep learning methods for the ligand pose ranking. And for visual inspection, we have other experts like Bu Yifan and Sun Jinyuan. And for one of the RNA ligand binding complex, Dr. Xiong Peng built the model for us. And for the optimization part, we have Wang Zecheng and Dr. Li Weifeng, Dr. Wei Yanjie. They developed a deep learning based deep MSD optimization method. And I would also like to thank our co-found team for the support. And that's all for the presentation. Thank you.